Hello, my name is Isabella and I will be your host for another mathematics video brought to you by RJ. In the previous video, I derived the function for producing elementary anti-symmetric polynomials and used it to determine if 10 has a friend. If you haven't watched it, I suggest watching it now. I also briefly described what it does and compared it to the function for producing elementary symmetric polynomials. But what exactly is an elementary anti-symmetric polynomial? Let's take a deeper look by first reviewing what is an elementary symmetric polynomial. This is the function for producing an elementary symmetric polynomial. Suppose we have a finite set of numbers. This function produces a polynomial where all of the terms are every possible product of those numbers. Let's do an example where each number is distinct, and for ease, let's just have 4 numbers in our set. We can write the symmetric polynomial in the form of a product. This, as I said, produces a polynomial that is the sum of every possible product of the 4 numbers. This becomes clearer once we expand this out. As we can see, we do in fact have a sum of every possible product of the 4 numbers. This is great. However, suppose there are numbers that are not distinct. In other words, there are duplicates of any of the numbers. As an example, we wish to construct a polynomial from 2 numbers, each of order 2. We can express the order of each number as an exponent as follows. If we expand this out, we obtain the elementary symmetric polynomial. Once again, we do have a sum of every possible product of the 2 numbers, given that there are duplicates. We could have also gotten this by this polynomial up here, using substitution. As we can see, some of these terms have coefficients that are not 1. This is a property of elementary symmetric polynomials. In the previous video, I mentioned that this is the key difference between elementary symmetric polynomials and elementary anti-symmetric polynomials. Elementary symmetric polynomials count certain values of terms multiple times, depending on the order of each number. Elementary anti-symmetric polynomials, on the other hand, do not. The coefficients for elementary anti-symmetric polynomials are always 1. The anti-symmetric version of this polynomial is each term has a coefficient of 1, and we still have every possible product of the 2 numbers, given that there are duplicates. Why is this important or helpful rather than the symmetric version? In the previous video, we were working with primes and factors. Natural numbers may have duplicate primes, but they do not have duplicate factors. If we use this symmetric polynomial, we would be overcounting. Each term is a factor, which is a product of primes. In other words, we would be counting certain factors twice, 3 times, 4 times, or more. With the anti-symmetric polynomial, we are ensured we are counting each factor only once. Can you think of other purposes for elementary anti-symmetric polynomials? I hope you enjoyed the video. Thank you for watching.